Alright people, welcome back. So, in today's episode we're dealing with problem 931, minimum falling path sum. And again guys, let me read this problem, but again you see grids in here, so I think we're gonna have the same usual approach. So given an n times n array, okay, so it's a square. It's a square of integers matrix. Return the minimum sum of any falling path through matrix. So again, we have to return a minimum path of a minimum sum of a path. A falling path starts at any element in the first row and chooses the element in the next row that is either let's say that we choose one is either directly below or diagonally left to right. Okay, so basically from 1 we can reach any element. From 2 we can reach just 5 or 6. Specifically, the next element from position row call will be row plus 1, call minus 1, row plus 1, call. Or row plus 1, call plus 1. Easy, guys. Very easy. So what, like the row is always row plus 1. What changes is the call. Guys, can I say that this means this is basically the repetition of the triangle? And if not, it's easier. Because, yes. Yeah. So, okay. My idea is the following. We compute the minimum path for every single element. And so basically the minimum path, of course, for the first row is going to be 2, 1, 3. Then what's the minimum path for 5? It's basically the minimum between all this, we sum 5 plus the minimum between the minimum path that gets to 2, 1, or 3. So this is going to be 6. Here is going to be 7. Here is going to be 5. And then these are initialized as the minimum between, okay, you know what's the story. We already solved other like 5 problems like this. So I think what really matters is how to deal with the edge cases. So for example, if I have a 7 here, so if I am the first index of this row, I can't take the index because I can take 3 values, but just 2 because this value does not exist. But I think we dealt with that last time. So I think I know how to deal with that. So we have a matrix n times n. So I believe now we can say something like n is equal to the length of the matrix. And then we can say something like for I in range n. So now I want to access the first row of the matrix. And then of course I want to do for j in range n. And then what I want to do is matrix, actually better to do range 1n because I want to skip the first row because we already have the values initialized with that. So matrix I, j is equal to, I want it to be matrix ij. So I want to sum to the value in the matrix, the minimum between the matrix, and now the column must be I minus 1, and now the row can be j minus 1, or it can be j, or it can be j plus 1. Yes, this thing here. Now let give us a bit of space. Okay, now this can be done only if this is a central value. So I must add an if statement, like if j is equal to 0, then of course I want matrix ij to be matrix ij plus, and I want to remove this element because of course I can't have an element minus 1. Now if instead j is equal to n minus 1, I want the opposite. So I want to take into account j minus 1j but not j plus 1. And then finally, if it is a central value, I can do the usual thing. Okay, now with this done, what I can do in the end is just return matrix n minus 1. Sorry. I must return the minimum between all the values in the last row, which is in this case n minus 1. So I believe this must work. Yes, this is basically the repetition of what we did with the triangle, and it works. So since it's basically the repetition, what I believe is that there must be a better solution. Otherwise, literally, we just did what we have done with the triangle. So let me think a bit. Okay, let's see if there is any hint. There is no hint. I said, it feels very strange, but since the problem is exactly the same as the triangle, I don't feel that they're like, even though I'm very surprised that the two problems are basically the same, they are inherently identical. So I don't think how is it possible that we have an ON solution here and ON squared solution for the triangle. So maybe what we can try to do instead is to try to optimize a bit these if statements. So I don't know, maybe so for example here we can do, instead of j like all of this, we can just write j minus 1 to j plus 1. This should work anyway, right? No, it doesn't. It doesn't, because maybe we need j plus 2. Yes. Okay, now I can do this also here. And actually maybe like this way I can avoid using the if statements, because what if I write down something like I want the maximum between j minus 1 and 0, and I want the minimum between j minus 1 and n minus 1. No, n. And then I'm done. I can avoid everything, right? I can avoid completely the if statements, because I am already taking everything into consideration at the same time, and it's very elegant now. Okay, did we improve anything, or did we just make the code shorter and less interpretable? I think actually we improved something, even though like it's now like more as like a sort of attempt to make it a bit more elegant, even though the complexity is the same, because of course we're avoiding using a lot of if statements. And so yeah, I think this is actually the real, very super optimized, elegant solution. So guys, I'm really happy because we're going pretty fast with these dynamic programming episodes. So at this point, thank you very much for watching this video, and see you in the next episode. Bye bye guys.